Hey there peeps! Work and energy. Work has many definitions that we use in our everyday lives. For instance, I worked really hard on that assignment, meaning effort. Work could mean effort. Or I went to work and I got paid $10 an hour to do these particular tasks for an employer. Another definition of work. Well, work in terms of physics has a very specific definition, and later on we're going to relate it towards a concept of energy, how much energy an object has or how much energy it takes to get something to move at a particular velocity, for example. All right, so work is this. It's related to forces and displacement in physics, and so it's when a force pushes or pulls on an object parallel to its displacement, that force is said to perform work on that object. Mathematically, it looks like this. Work equals force parallel times, well, delta x would be our displacement. This symbol here is not 11, it's actually the parallel symbol. So we have the parallel symbol in math and also the perpendicular symbol. This is the parallel symbol, so we recognize that that force is going to be parallel to the displacement that it moves. Okay. The units are newtons times meters if we look at force and displacement. However, that's not what we call this unit. It's not a newton meter. We reserve that for the concept known as torque. Torque is also newtons times meters, or newton meters, and torque differs in the fact that instead of force parallel, it's actually the force perpendicular to what's known as a lever arm with respect to a fulcrum, okay? So torque is actually made up of force and distance also, but it's a different application of it. Here we've got force parallel times the displacement, so we don't want to confuse the two. And so what we do is actually change the name of the unit. They actually name this the joule, named after, well, James Joule, who's a famous scientist who worked a lot with the discovery of energy and heat in particular. So over here, we also have a look at what happens if there's an angle on that force. And if that were to be true, then the force times the cosine of that angle times the displacement would give us the amount of work done. In the case where there's no angle, where theta is 0 degrees, the cosine of 0 degrees is just 1. So we just have the force times delta x, just like it looks over here. Force parallel times delta x, the displacement. Work and energy is a scalar. That's actually kind of cool because it's much easier to use. Let me give you an example. It would not be correct to say you have 5 joules of energy or you have done 5 joules of work north. That does not make any sense. It does not have a direction associated with it because it is a scalar value. It has magnitude only. So you can say an object possesses 5 joules of energy, or we have given it takes 5 joules of energy to move this object 10 meters per second or something like that, okay? So because it's a scalar, in some respects it's going to be easier to work with than some of the other quantities. Well, I'd like to run you through 3 examples. One that's very simple, that is a frictionless one with no angles. The next one has an angle and friction, and then the last one is an inclined plane. We're going to calculate the net amount of work in each situation. Okay, let's do it. And so here's our simple example. It's just one with a frictionless surface. So we're going to pretend that this is pure ice, like totally frictionless. It's not going to give any resistance. There's no nubblies whatsoever. So it's also fictional as well as frictionless. Frictionless, but fictionful. We have a crate of kittens. They're very tiny ones. Uber tiny kittens. 5 kilograms. All right. There's an applied force of 100 newtons. And the displacement will be 8 meters from here to here. We can consider this to be our origin, and this is 8 meters away from that. And so it'll be here after it's pushed with this 800 Newton force. The coordinate system we have is as follows: positive x to the right and positive y upwards. Okay, it's a pretty simple calculation here. We got work equals force parallel times delta x. Now the cosine of 0 degrees, because there's no angle, is 1, so it's just the force times delta x. very simple. We have that here. 100 newtons times 8 meters gives us 800 joules. That's the net amount of work that has been applied to this box. Okay, so the work has been performed by this force on the box of kittens, and it is 800 joules worth of work. That's what it is. We can say that at the moment over here, this object possesses 800 joules of energy. The type of energy is the energy of motion, since it's been put to motion, known as kinetic energy. So it has 800 joules of kinetic energy. Let's move on to a slightly more interesting example. Example 2 has a friction-full surface and item. So we got the nubblies interacting here between the 5 kilogram box of kittens and the surface itself. Okay, we also have force applied pulling at an angle. So with respect to that, what's happening here is that this force applied, the cosine part of it, parallel to the displacement, which is exactly in the x direction. Okay, makes sense. Displacement is in the x direction. So delta x is 8 meters, and this will move over here. Here's our coordinate system that y is positive, y is up, and positive x is to the right. Here are the values for that describe the physical parameters of the crate and the forces and the coefficient of friction. So we got mass is 5 kilograms, theta, the angle is 40 degrees that's being pulled. Force applied is 100 newtons, just like it was. Mu kinetic is 0.4. Remember, there are no units for mu, it's just a ratio of two forces, force normal and force of friction. And delta x is 8 meters, as it was before. So here's the free body diagram. I should actually kind of put this all on a dot, but for this case, I decided to use a box. The angle is here, is with respect to the horizontal. Of course, it's on a surface, so there's a normal force, and it's going to play a role because we have friction. And of course, the weight of the crate is going to be the force of gravity, which is mass times gravity. The acceleration due to gravity, 9.8 meters per second squared. And then the force of friction will try to oppose the motion forwards, as friction always does. When friction opposes that motion, it's going to be also, interestingly, parallel to the motion itself. So while the applied force is at an angle, the frictional force is in the same direction as the displacement. So there we go. Let's look at it mathematically. So we've got the net amount of work is going to be in the positive direction. We've got force applied times the cosine of the angle times delta x. That's this way. In the negative direction, we have friction, so it's minus the force of friction kinetic, and that's also going to be times the delta x, the displacement. What we're going to see here in a moment is that the friction actually has a negative energy associated with it. It's trying to steal that energy away. The force is in the opposite direction as the displacement of the object. Therefore, you're going to have negative energy. Well, let's take a look at the force friction. How do we find it again? A little review. It's mu k times force normal. Well, what is that? Okay, if we look at the free body diagram in the vertical direction, the y direction, we have force normal in the positive direction minus mg over here in the negative direction, plus force applied times the sine of the angle. Remember, we're pulling up over here, so it's going to lift the box of kittens up slightly off of those nubblies, so they're not squashed as much as before. Therefore, that is going to influence the normal force. And this is going to equal 0 because there's no acceleration. By definition, if you have a normal force, it means you don't have any acceleration in that direction because the object is going to be laying on the surface. It's resting on the surface in that direction vertically, right? So this is equal to 0, otherwise it would be AY, mass times AY, all right? If I solve for force normal here, force normal is mg minus force applied sine theta, okay? So I'm going to substitute that in here. Boom, here it is. That replaces force friction kinetic, mu times force normal. So now it looks like this in the second line. The net amount of work is force applied cosine theta delta x, same as before, minus mu kinetic, parentheses, mg minus force applied sine theta, that's the normal force, times delta x. I took the liberty of checking to see if we have all the values, and we do. All of these are known, which is great. That means we can calculate it through and get a number. So that's what I've done over here. I plugged in the numbers, and this part here is 613 joules. That's the force applied in the horizontal direction. Notice it's less than it was before because we're at an angle. Some of that force is obviously not going horizontally, some of it's also going vertically too, upwards. So it's only 613 joules instead of the 800 we had last time. And also, we've got this frictional part here, negative 136 joules, stealing away that energy, okay? Friction, it does that. It's going to, what's called dissipate the energy into another form. That other form actually is in the form of generally heat and sound and vibrations. Okay, so when you drag something across the table, you can hear it scraping. Actually in the surface, if you were to have a very sensitive thermometer, measure the temperature, it would go up a little bit because of the, hey, do this. Whew. It's actually kind of chilly in this room anyway. So by doing that, you feel that heat is generated with the friction of your hands rubbing, okay? So that's the idea, that the energy of those nubbly scraping, some of it turns into sound, you can hear that, some of it turns into heat, okay? You can feel that too. And that's what this is. It's actually stealing energy away that would otherwise go into the motion, the kinetic energy of the box of kittens. Okay, so if we crank this through, the net amount of work is just 613 minus 136, or 477 joules, significantly less than we had in the very simple example. Okay, very good. We're gonna do one more with the inclined plane. So here we go. Voila, the inclined plane with friction. Here it is. Okay, so it's drawn out here. We've got our free body diagram. What I've done is considered, based on the information we have in this list over here, we've got the same mass as before, 5 kilograms. I even used the same angle as I did before, but the angle means something completely different. It's the angle of the ramp with respect to the horizontal, okay? Mu kinetic is the same as before, 0.4, right, no units, right? You picked that up, I saw that, very nice. Delta X is 8 meters, same as before, but it's that 8 meters represents the sliding down this ramp, okay? So we're gonna assume that static friction isn't enough to hold this, that it's going to be sliding or it's set into motion, okay? So we're just gonna deal with the kinetic part here. The free body diagram looks like this. So we've got mg straight down. We have the force normal that's going to be perpendicular to the surface. The surface is on an angle, so it goes this way. And our coordinate system is rotated to reflect that. So we've got the motion down the ramp. That's the positive x direction. And perpendicular is the y direction. That's where force normal points. And the force of friction will oppose it in the negative x direction up the ramp. Delta x, again, is the same as it was before, 8 meters down the ramp. In blue, I've done the vectors for the gravitational components, breaking them up according to the coordinate system. The free body diagram itself is just the black vectors, but the other ones are nice to draw for calculations when you rotate the coordinate system. So we have down the ramp, mg sine theta, this is a review from before, and down, pushing down the surface, squashing those nubblies between the crate of kittens and the surface of the ramp is mg cosine theta. So let's take a look at this mathematically now too. The net amount of work is going to be, well, in the positive x direction here, we've got mg sine theta times delta x. So here's the work done by the component of gravity that wants to slide this down. All right, so we know that gravity would want to accelerate something at 9.8 meters per second squared if there's no angle associated with it, it's just straight down. But in this case, as we know, it's going to be responsible. It is the force that's responsible for sliding it down the ramp. All right, so mg sine theta. Minus force of friction kinetic times delta x. So that's in the negative x direction here, which is why we have the minus. Well, again, what is the force of friction kinetic? Like we've looked at before, it's mu k times force normal. All right, there are no other vertical forces except for mg cosine theta. So there's no like other angle and stuff like that. So the force normal will equal mg cosine theta. And so that's what we have here for force normal. So the whole thing for friction is mu kinetic times mg cosine theta. So we're going to plug that thing in here. And so here we go. The net amount of work is mg sine theta times delta x minus mu kinetic mg cosine theta times delta x. And you're going to say, but I thought the force friction or force times cosine theta is what work is times the displacement. Well, hang on, that's when you change the angle relative to the displacement, okay? The force here is parallel. It's what you want to consider is what force is parallel to the displacement, and it's this one. That's it, mg sine theta. So that's the one we're going to use, okay? It's only when the applied force is at an angle that we worry about that cosine term. So just go with the free body diagram, let it lead what we write, and it will look like it should, okay? So here we go. I note that all of these quantities here, all of those values are known. I've checked them off. Therefore, we can actually process this and calculate it at this stage. And so that's what I've done. We have 5 times 9.8 times the sine of 40 degrees times 8 gives us 252 joules. I didn't mention this last time, but whenever you have g, you should just put in 9.8. We already took care of any negatives with the coordinate system in writing the equations from before, okay? So don't put in the negative sign there. It will screw you up. It's just 9.8, and it was the same for the example before too. And so over here, we have negative 120 joules by cranking this out. And the total is 132 joules, so quite a bit less. This has a lot less work that was performed on it because in this case, based on this angle, we didn't have all that much force compared to the force applied. Of course, it was arbitrarily 100 newtons. There's probably a lot less than 100 newtons here, so that's one of the reasons that this is much lower. And we have, friction stealing a pretty good amount at negative 120 joules, right? Okay, so when we add these together, the net amount of work is 132 joules. So it will have that much energy, and so there'll be a way to actually calculate its velocity using something called kinetic energy. So it has this much kinetic energy when it's at the bottom, when it has moved down the ramp a distance of 8 meters. It's a pretty long ramp, but that's what it is. All right, so those are the 3 examples. Work, energy, we're gonna evolve these concepts further. We're gonna talk about things like potential energy, it's like gravitational and whatnot. We're gonna talk about rotational energy, we're gonna talk about power, and it's gonna get very, very interesting, and it's very connected to the world we live in where we rely on energy all the time. Okay, Morad out.